Rapid spanning tree protocol is where we want to be, right? But you need to understand plain old spanning tree protocol and how slow it is to appreciate the rapid part of rapid spanning tree protocol. So in this video, we'll go over the age-old slow spanning tree, and in the next video, we'll appreciate why we love rapid spanning tree. Let's jump in. So in the CCNA Cert Guides, Volume 1, there's a chapter on concepts for spanning tree. It has 3 sections, and this video is about the second of those 3 major sections, with details specific to spanning tree, but not to rapid spanning tree. And those details happen to be about the, relatively speaking, slow convergence actions of spanning tree protocol. And the last section is about the relatively fast convergence features of rapid spanning tree, all right? So in this video, I'm going to approach the topic like this, which may vary from that section in the book, all right? So we'll talk about direct spanning tree protocol convergence. That is, the switch that we're examining has direct knowledge of the failure. Then I'll do 2 different demos of an example of that. And then we'll talk about this idea of indirect spanning tree protocol convergence. That is, a switch does not have direct knowledge of a change. The change happened at least one switch hop away. So the switch that's going through this convergence event has to be more cautious, and it takes longer to converge. Then I'll demo an example of that. All right, so we'll go through and along the way, we'll catch all these weird things that make spanning tree protocol slow down and converge more slowly than its newer, faster cousin, RSTP. Of course, as always, stick around to the end, and we'll be in study group together. I'll give you my advice on where to focus on this topic after you get through this video. I'll talk about how you can review and revise here at the channel and how you can do the same from the official cert guide. All right, let's get into it. First, let me make sure you're clear on some terminology. STP, without the R in front, it was first defined by the IEEE in the 802.1d standard. Came out in 1990, as it turns out. And then later, the IEEE made an addenda to that standard called 802.1w and defined rapid STP or RSTP. That was about 10 years later, call it year 2000, 2001, somewhere around there. So about 10 years later, they said, we want to improve this. And the main thing they improved is how fast it converged when something changed. Then, just as a bit of trivia, but also important if you want to read about this straight from the standard, is that the IEEE moved the spanning tree protocol details into the VLAN and VLAN trunking standard 802.1q. So if you want to look for the specs, look for the 802.1q standard. That happened in the early 2010s, so call it 2010. So about 10 years difference in time approximately from the original definition to adding RSTP to then moving the details over to 802.1q. All right, so that's a bit of the context of the terms. We're focused on STP without the rapid part for this discussion. Now, throughout this discussion, I'm going to use the same topology throughout in this video and in the next one with the same interface IDs. So the links connected to 3 hosts are all gig 1011, and I mostly ignore them. Then the links between the switches, those are the ones that are going to become root ports and designated ports. Here's what I've done. Here on switch 1, notice the interface ID ends in 2. That matches the switch number on the other end of the link. Gig 103, 3 matches the switch number on the other end of the link. Over here on switch 2, interface ID ends in 3, matches switch 3. Switch 3's interface that ends in 2 matches switch 2, and so on. So that's my convention for how I've numbered things there. I've also set up the config that I'll use in demos and in these slides to always make switch 1 be the root switch, and then set it up so that the root ports are those that you see marked there on switch 3 and switch 2. And that we end up with these designated ports that you see marked in the slides. And the one port that doesn't have a port role then is switch 3's right-hand port, this one down here. And that's the one then that ends up in a blocking state because it has no role. All right, so that's going to be our stable, steady state before we launch into some failure that causes a convergence event in all our demos coming up. Now, that could be stable for months and months and months. And when that's happening, what happens is that spanning tree says, hey, the root should send out hellos, and then other devices should send out hellos as well. And those flow like this. the root will send its hellos out all its designated ports like these. And over here, switch 2 is going to forward that hello out its designated port. So basically, all the designated ports forward these hello BPDUs out. But the switches don't forward hellos on their root ports. All right, so basically forwarding hellos on the designated ports, and that's where the hellos are flowing steady state forever and ever until something changes and forces a convergence event. Those hellos, by the way, those flow every 2 seconds by default based on a hello timer. And there's another variable that's based on hello timer called max age. It's 10 times the hello timer or 20 seconds by default. All right, so let's talk about one example of what could break and how spanning tree protocol deals with that and how fast it converges. So we're going to think about things from switch 3's perspective because switch 3 has the one blocking port, and if something breaks, it's going to need to move that port from a blocking to a forwarding state, right? And that also means that it's going to probably need to move that port from a no role to some role like root port or designated port, right? So that it'd have a reason to move it to a forwarding state. So we're going to break that left-hand link. And because we break a link that's attached to switch 3, that from switch 3's perspective would be a direct failure. And that means switch 3 can act immediately. All right, switch 3 has direct knowledge, hey, my root port failed, and I'm confident I know it failed because my interface is down. Let me act. And the thing it'll do is it'll keep seeing these same messages that are still flowing. Remember, those arrow lines are showing us hello BPDUs that are still flowing in the network. And switch 3 will receive that here and say, hey, you know, this left-hand link, it's down now, but I'm getting this hello from switch 2, and it's telling me switch 1 is the root switch. That's my only path to the root now. That's got to be my best path to the root. I'm going to select a new root port of gig 102. And that can happen relatively quickly, all right, as soon as the interface is down. What happens behind the scene, though, is switch 3 can't use that port in a forwarding state yet. There's this idea that says, hey, if we're moving from blocking to forwarding, we want to be cautious. We want to make sure and not use the forwarding state too quickly because that can cause temporary forwarding loops. So here's the logic that gets applied. Once switch 3 chooses to place the port in a root port role, it puts the state in a spanning tree state called listening. And in listening state, it just says, hey, I'm listening for frames, but I'm not learning their MAC addresses. I'm not forwarding the frames. And it stays there for forward delay seconds, which defaults to 15 seconds. And then after that 15 seconds, it moves to learning state, 15 seconds, again, based on that same forward delay time, and then finally reaches forwarding state. So it's an extra 30 seconds to move from blocking to a forwarding state. All right, so that's normal with plain old 802.1d spanning tree protocol, and unsurprisingly, rapid spanning tree protocol improves on that quite a bit. All right. Next up, while that listening and learning state stuff is happening, the MAC table gets timed out. So whenever that happens, the aging time gets lowered to the same number as the forward delay of 15 seconds. So at the beginning of listening state, let's just say we had these two MAC table entries and they were listed off port gig 101. That was the original root port that just failed. So by the end of the listening state's 15 seconds, those entries would have timed out and been removed from the MAC address table. So we've gotten rid of any MAC table entries that would be old and stale and make no sense now that that link was failed. And then by the end of learning state, in learning state, no frames are forwarded, but you can learn MAC addresses. The switch will learn MAC addresses. So those same MAC addresses could already be learned off of the port that's still up now, but ready to use for when we reach a forwarding state. Next, I'm going to demo that same convergence event. So there's some config here, and I'm going to tell you about it, but we haven't gotten to the configuration of spanning tree yet in sequence, but it's pretty easy to understand. On switch 1, this command says you're most likely to be root, and we're going to make sure switch 1 becomes the root switch with this first global command. And the second one is the command we use to say use spanning tree rather than rapid spanning tree. All right, turns out PVST is per VLAN spanning tree, and that's just the acronym Cisco uses for the old spanning tree protocol. And we do something almost identical on switch 2, except we use the word secondary instead of primary, which says it's second most likely to be the root switch. So switch 1 and switch 2 are most likely to be root, and it turns out that also makes switch 2 win any tiebreakers. So it beats switch 3 to become the designated port in our topology. Switch 3 has just got that command that says, yeah, use old spanning tree protocol, not newer rapid spanning tree protocol. You don't really have to go understand all that, just accept it for now. But when you learn the config, you've got it there in your back pocket. All right, so what do we have here? We've got the same topology. Switch 1 is root. Switch 2 is not. It's got a root port. It's going to be designated port on this link down to switch 3. Gig 102 is the one that's going to be in a blocking state to begin. We're going to fail this link because you're going to see me go up to switch 1, and I'm going to shut down this gig 103 link during the demo. Then we're going to do show commands down here on switch 3 and see this gig 102 port become a root port, and we're going to see it go through this listening and learning state. All right, that's where we're headed. Let's go do it. So here we've got a terminal window connected to switch 3, and if you do a show spanning tree command and look down at the bottom, we have gig 01 and gig 02, and those are the ports off switch 3 that are connected to the other switches. We see gig 01 is indeed the root port in terms of its role. And then we've got this other port, gig 102, which has no role as far as spanning tree protocol is concerned, but in a weird quirk, iOS will list it as an alternate port. That's an RSTP feature we'll talk about in the other video. But notice gig 102 is in this blocking state that you see down here. So it matches the topology we've been talking about all along, all right? So we're going to see this gig 102 change to be a designated port and then go through the listening and learning state. So I'm going to repeat this command over and over during convergence, and we're going to look down here at the bottom to these lines, and particularly the line for gig 102. Now over here, we've got switch 1 in config mode, and I'm going to do a quick show interfaces status and see that gig 103 and 102 are both in a connected state to start. All right, and we'll get rid of that and see that we are in config mode for interface gig 103, and I'm going to shut down that interface here in just a second. There we go. It's got the shutdown command ready to go. Now, for perspective, I'm going to put a counter over here on the right and keep that on the screen. So here we go. I'm about to click the enter key to do the shutdown command and then start the stopwatch. There's the shutdown, there's the start, and here I am. Get the messages that the link is down, and I repeated the show spanning tree on switch 3, and now it lists gig 102 as a port role of root. So that happened really quickly, obviously, right? But now it's in a listening state. We're already up to 20 seconds, as it turns out. Hit the up arrow. We're now in a learning state, and hopefully when we get just past the 30-second stage, we'll be in a forwarding state. Let's see, we're in the low 30s. Did we get there quite yet? There we are in a forwarding state. So that matches what we've been talking about all along, right? So I'm going to hit stop there. And that's our demonstration where we saw an immediate action after the failure of the interface. Here's the link going down, and as soon as I could issue the show command, we've already picked a root, or switch 3 has picked a root port role, place the port in a listening state, then we got to the learning state, sorry about that jump in the screen there, and then the forwarding state, just like we talked about. Next, we're doing the exact same scenario again, but I've got debugs turned on the switch. So we're going to fail that other link by shutting down this interface. We're going to see switch 3 choose a new root port, gig 102. We'll see it go through the listening and learning states, but the debug messages are going to tell us that that's happening. There'll be timestamps on those debug messages, so it'll be more obvious. To get those debug messages, we're going to use these exec commands, and on switch 3, debug spanning tree events, which says, hey, give me some messages when spanning tree events happen. And when we're tired of seeing those, undebug all, we'll turn off all debug messages. You'll see in the demo. Let's go repeat the same scenario and look at those debugs. So I've reset everything back for the demo to the starting point of where it was before. And just to confirm it, if we do a show spanning tree here on switch 3, gig 102 is back to a blocking state. It says alternate, that's that RSTP term, but it doesn't have any spanning tree port role. And gig 101 is the root port in a forwarding state. And that link that we shut down before, it's brought back up again. All right, so everything's good to go. And now we're going to shut down that same port, but this time we're going to focus on those debugs. So let's just get the debug going. Debug, spanning tree, events, and do that. So now when spanning tree events happen, we'll see messages here. So instead of me doing all these repeated show commands, let's just sit back and watch what happens here with those log messages when we go shut down the port. So just to confirm, it's interface gig 103 on switch 1. And we're going to do a shutdown command to bring the port down. And I'm going to start the timer at the same time. Here we go. Shut down, start timer, back to switch 3. We're just watching for messages. So we've seen a few, and at about the 15-second mark, we should see one that says we're moved to a learn state. There it is. Gig 102 is now in a learning state. When we get just past the 30-second mark, we should see one that says forwarding state. And at that point, I'll circle back and talk about them for a moment. Here we go. All right, there's the last one. I'll stop the timer. So what did we see with these log messages? Well, it said, hey, we've got a new root port in VLAN 1, gig 102. It's got a cost of 8. That's kind of interesting, right? And we see that we've moved gig 102 to a listening state, and it gives us a timestamp of 33.579, so 33 seconds, point something. And then if we go further down to the one that says we've moved that port to a learning state, it was 48 seconds, right? So 33 to 48 is 15 seconds later. 48 to 03, 15 seconds later to move to a forwarding state. So that's consistent with our forward delay time of 15 seconds each in those instances. And of course, if we did the show spanning tree command, we're going to see that port now is a root port in a forwarding state, just like we've been talking about all along. By the way, this video is sponsored by me and my books. If you don't happen to have them yet, and you click that link or scan the QR code and go to my link tree and click the products link there and buy the books there, you don't have to spend any more money, but those sellers happen to give me a few dollars back from the sale. It's a great way to say thanks and support the channel, and I'd very much appreciate it. All right, back to the content. So let's talk about a different scenario. Here's switch 3, and we're going to focus on how switch 3 thinks because that's where this port is that's in a blocking state, and it's going to need to change. But let's imagine that top link between switch 1 and switch 2 fails. From switch 3's perspective, that's an indirect failure. That is, switch 3 doesn't know that any interface has failed, right? So how in the world does switch 3 even know anything has changed? So it turns out spanning tree has all these things built into it to tell all the other switches that are further away that something has changed. So remember how these hello BPDUs have been flowing, right? Well, there are bits in the hello BPDU message that signify, hey, there's a topology change. It's a topology change indicator bit. And there are even whole BPDUs that detail changes, all right? So there are messages and bits that are meant to signify change has happened. So switch 3 may receive different info than before, less info than before, bits that mean the topology has changed. But with spanning tree, which was created in the mid and late 80s, all right, and a different era. The goal was to give us a loop-free topology, but loop-free was hugely important. So it needed to be cautious. So the goal was to converge when safe, but not before it's safe. And if there was ever a question of a move could cause a loop, you don't make the move. All right. So that was, for instance, why you go through listening and learning and take your time to go from blocking to forwarding, or at least why the protocol did that. So here's spanning tree's reaction for a switch that hears about an indirect failure through these different messages and bits and messages. It's to wait. And it waits max age time before making new decisions. And the idea is, let's let the network, stabilize. If things are changing, let's let it all change. Let everybody hear about the change before we decide to act on this new information. All right. So that's the goal. And max age defaults to 10 times hello, and that's 20 seconds. So by then, hopefully everybody knows the details of what's happened. And then you could say, pick a new root port, or pick whether that you want to be a designated port, which will be the case in this particular scenario. So what happens in this case? Well, we're back to our standard with everything working, and that top link fails. Switch 3 gets all these different bits and messages that indicate a remote failure. So from switch 3's perspective, it's an indirect failure, and it's going to wait 20 seconds before it acts. But switch 2 has a direct failure, right? An interface went down, its root port went down. So it turns out in this case, look at the notes up here. Switch 2, direct failure, reacts, and it's not getting hellos from the root anymore, so it claims to be root. That's all it can do is say, hey, I am root. So it's sending messages down to switch 3 saying, I am root. I have the best bridge ID. Switch 3 is ignoring that for 20 seconds. And then eventually after 20 seconds, switch 3 says, hey, I've heard about all these changes happening. I'm looking at this hello from switch 2 with switch 2 claiming to be root. I'm looking at the hello from switch 1 with switch 1 claiming to be root. Which one's better? Well, it turns out switch 1 is better. How do I know? Well, before all this happened, switch 1 was better. Switch 1's bridge ID is still better. So switch 1's still the best in terms of the bridge root election. So switch 1's the root. What's the net result of this? It turns out that switch 3 in the designated port election on this link, switch 3 is going to have a lower root cost in this part of the election. So what happens with all this? Well, switch 3 is going to win the designated port selection process with switch 2. Switch 2 is going to end up with a new root port, accepting that switch 1 is still the root switch. That's your new spanning tree topology. Now, the designated port, as soon as switch 3 says, hey, this port is designated, guess what? It doesn't immediately forward. It's got to go through 15 seconds in listening state and 15 seconds in learning state. Whew. So the convergence is a little slower. We had that extra wait of max age time before switch 3 would act. And then once it chooses to be a designated port here, we've got to go through those two interim states before reaching forwarding state. For the final demo, I'm going to demo that exact same thing. We've got our usual topology. I'm going to fail that top link. I'm going to get into switch 1 and shut down gig 102 to shut down the link. Then I'm going to sit down here at switch 3 with a debug on and with show commands. And we're going to wait that 20 seconds for max age, and then for that 15 seconds each in listening and learning state. So watch out for the 20-second mark, then the plus 15 or 35-second mark, and the plus 15 seconds more at the 50-second mark for some big indicators in the demo. Let's go do it. So let's do this one more time. We have the same starting point with all the links up. So if we do another show spanning tree command on switch 3, just to confirm, gig 101 is the root port again, and it's forwarding. Gig 102 shows up as an alternate port and blocking. And again, alternate port's a rapid spanning tree protocol thing. We're using spanning tree protocol, so it's really a port with no role at this point, but it is indeed blocking. Gig 102 is the one that we're going to move from a blocking to a forwarding state. But in this case, it's going to be an indirect failure from switch 3's perspective. We're going to fail switch 1's link to switch 2. So we're going to get into config mode for interface gig 102 and shut it down, but not quite yet. I want to turn that debug on again. So debug spanning tree events here on switch 3, and I'm just going to have a sit back and watch those messages for a little bit. Now, from when I hit the shutdown and the far away link, the indirect link fails, this switch 3, is going to wait 20 seconds. So watch the timer for about the 20-second mark, and then you should see this gig 102 port get to a listening state, and then 15 seconds later at the 35-second mark, learning state, and then 15 seconds later at the 50-second mark, reach a forwarding state. All right, so 20, 35, and 50 seconds is where I expect to see those things. So here we go. Let us do the shutdown and start the timer now. So we're hearing some messages according to the debug messages. That switch 2 sending us new BPDUs, but this local switch SW3 is ignoring them. And here coming up on the 20-second mark, max age should be expiring, so switch 3 can act, and it's placed a port in listening state. If you saw that one there, we're getting some messages about topology change notifications. So here we're coming up now on the 35-second mark, so that port should get to a learning state here right now. There it is, learning state for gig 102. And finally, it's going to get to a forwarding state here in just a few more seconds at the 50-second mark. Dun, 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 dun. Poof. There it is. And I'm going to turn off the debugs and do a show spanning tree command again. And we see gig 102 is now a designated port, as we mentioned just a few moments ago in the PowerPoint slides, and in a forwarding state in this case. And we saw those messages come through, the debug messages, telling us about those transitions at the correct times. So in Chapter 9, we're talking about concepts in spanning tree, and we're talking about the things that are true of spanning tree and not rapid spanning tree, which are the convergence features. So you want to use rapid spanning tree. You don't want to use this old slow convergence stuff. So that's the important part. We really want to know it so we can recognize how much better the rapid spanning tree features are. So we don't really have any review things here at the channel for this, but if you've got the book, read over that section. It's just a few pages. It'll give you some good perspective and another look at it so you get a richer view at things. However, with the next video that focuses on rapid, we will have an ad hoc lab to go with this and give you a chance to experiment with this convergence, both with spanning tree and rapid spanning tree in Packet Tracer. This is one of those cases where you should go ahead and watch the next video right away. Click on the left to do that. That's the associated video that focuses on rapid spanning tree protocol and its convergence features that are different than plain old spanning tree protocol. Then on the right, click there to go to the ad hoc lab where you can see both spanning tree protocol and rapid spanning tree protocol convergence in Cisco Packet Tracer. Hope you enjoyed this one. We'll talk to you soon.